In this section, we're going to discuss a variation of our random forest. Let's say we use our random forest model and we still have some overfitting, or we have some overfitting that we want to reduce. So we have a high variance, so let's discuss the way we can reduce the variance for the model. Let's go back to our random forest and let's make sense of how the model is trained. Remember that we're going to consider a subset of our features, and this is going to prevent highly correlated trees. We don't want trees that all look like each other. We want a diverse set of trees. So to perform a node split, we're only consider a subset of our features. For example, we have 4 features. Let's only consider a random subset of 2 to perform a node split. So we're going to consider these 2 features. And the way it works, as with any decision tree, we're going to look at all the different values for each feature. And we can use these to construct a threshold. In other words, consider all the different values for each feature. We're going to consider them as using to formulate our yes or no question, or our question with a yes or no answer. And through these 2 features, and however many distinct values we have for each feature, we're going to try them out and see which one we should use that's going to reduce our error metric the most. It's going to reduce our entropy, reduce our Gini metric, or if we're dealing with regression, the overall drop in variance. Now let's say through this analysis we figured out that using this feature here, this axis, and using this threshold is the best to perform our node split, to partition our space into 2 parts. However, what if we do a variation of this algorithm? We're going to still consider a subset of our features. So we have total 4 features. Let's just consider 2. And let's say for these 2 random features, we're going to do a random cut point. We're only going to look at one possible cut point, one possible threshold for each feature. So for one feature, this feature here, let's just randomly choose this cut point. It's randomly chosen. And let's say for this feature, I'm going to randomly choose this cut point. So now I have 2 candidates, only 2 candidates to use as my cut point, as a question to perform my node split. And then I choose amongst these 2, or between these 2, which one is the best one to use, which one will result in the greatest drop of my error metric. And let's say through just only using these 2 points, I've realized that using this threshold is better. Now, considering this variation of this algorithm, why do you think it works? Or what do you think it's doing? What do you think it's doing by only considering a random cut point for the subset of my features? I said earlier that this variation of the algorithm is going to reduce variance, is going to reduce overfitting. And it makes sense because now instead of considering all the possible thresholds between the subset of my features, I'm going to just consider 2. So what's going to happen is I'm going to move from overfitting to underfitting because my model isn't as adaptive. I'm not considering all possible cut points among my subset of my features. Just 2 random cut points for each of the subset of my features. So my model will tend to reduce the variance error, push it from overfitting to the underfitting spectrum. Are there any benefits to this variation of the algorithm? The fact that I'm only consider 1 random cut point for the subset of my features. Well, to best answer this, let's consider the time complexities for the random forest model. We haven't discussed the time complexities for random forest. We did so for decision trees, the standard decision tree model. Let's discuss the training and time complexities for the random forest. For prediction, we still have that our depth of the tree will be on order log of n. So if we have more estimators, all in parallel, then the resulting prediction time will be m log of n, where m here is going to refer to the number of estimators, the number of trees that make up my forest. So we go from log of n to m times log of n. So not too bad, that makes sense. If I double the number of trees, then I'm going to double the double the prediction time. Let's go ahead and answer the other question, is what is the training time complexity for a random forest model? And the way we answered that last time is that we understood that each node, we must consider each feature and all the distinct values for those features when deciding what is a good cut point. What's a good question to use to divide my space, to perform a split on the node. So we must consider all p times n combinations at each depth, at each layer of my tree. But remember with the random forest model that we're going to consider only a subset of my features to perform a split. And typically we're going to consider the square root of the number of features. Notice this, we can choose the log of the number of features as well. That's a hyperparameter we can tune for the model. But let's just say for this, I'm going to consider the square root of my features. So I'm going to consider square root of p times n, and then the other part stays the same, times the overall depth of the tree, log of n. But since I now have m estimators, I must perform this m times. So I should just put this under here. So my prediction, my training time complexity is going to be m times square root of p times n times log of n. And that's a benefit of only considering a subset of my features. Instead of p, now it's square root of p. So it's going to have, yes, I have more estimators, so that's going to take longer to train, but not so drastic if I consider all the features for each node split. And of course, this has the other benefit, the main driving benefit behind this is to construct a diverse set of trees. So a side effect is a better training time complexity. Now going back to the extremely random forest, notice there we're only consider we're not going to consider all the different values for each subset of the features. So we have m square root of p times log of n. So this is the extremely random forest, and this is just random forest. Because remember, when we perform a node split using the extremely random forest variation of the algorithm, at each node we're going to consider just a random cut point for the subset of my features. So it's not square root of p times n, it's a square root of p. So a benefit of using the extremely random forest is that it's going to have a better training time complexity compared to just the random forest. So there's two benefits. One is to reduce the variance error, but a side benefit is going to be faster to train. Let's go ahead and play around with the documentation. So for the extremely randomized forest, it's called extra trees classifier, extra trees regressor, whichever version we are using. So to ensemble, we're going to import random forest. Let's say random forest classifier and extra tree regressor classifier. Let's go ahead and run that and just go ahead and pull out the documentation. All right, it's always good to explore the documentation. Random forest classifier. And notice that our max features are set to auto. Let's see what that means. It says here that if we set to auto, it's going to consider square root of our number of features. This is in contrast to the standard decision tree model. If we look at the documentation, we see that if it's considered the max features set to none, that's equivalent to looking at, let's see, max features when it's set to none. Let's see, none optional, and max features equal number of features. So make sure you look at the documentation to get a better feel of these models. Let's see, extra tree classifier. So there you go.